In Chapter 9, we will be talking about the chain rule and how it applies to implicit differentiation and related rates. So thinking about what we call implicit differentiation, first of all, let's just think about the words explicit versus implicit. What do they mean in English? This is another one of these cases where mathematically words mean very similar things as they do in the actual language that they were taken from. Explicit means that something is given to me directly, whereas implicit means that the thing that I'm after is described somehow indirectly. And this applies to how we've been seeing functions so far. So far, we've been dealing with functions given directly or explicitly in terms of one variable. So we've always seen y equals blah, where that thing on the right had x's only. So all of our functions were given to us directly as y equals a function of x. But that needn't be the case. So for example, let's take a look at this expression. X squared, or a relationship, x squared plus y squared equals 4. That's not given in the form of y equals a function of x. Here we have y's and x's intermittently on one side or both sides of the equation. So if I had to take a derivative of an explicitly defined function, we already know how to do that. I'm going to take a derivative on the left-hand side, which is just y prime, and on the right-hand side, I'm going to apply whatever differentiation rules are suitable. Product rule, sum rule, whatever. But I have no idea how to take a derivative of something like this. So this is what we will call implicit differentiation, taking the derivative of a relationship like this without knowing the exact expression for y. We can always try to take the problem and reduce it to the previous one. So if we can solve this for y, then we have y given to us directly, and we can apply all the rules that we already have learned about. And then we're going to learn this new technique where we will be able to skip that solving step. So let's try both methods side by side to see how they compare. In the first method, I have to solve for y and then differentiate. Fantastic. So let me start with isolating y. So y squared is 4 minus x squared. And now I need to take square roots of both sides, which will of course result in the plus minus. So y is equal to plus or minus square root 4 minus x squared. So that means if I have to take a derivative of it, I actually do have to consider each case separately. This is really not terribly surprising, because if you think of what is the graph of x squared plus y squared equals 4? Well, the graph of that is actually just a circle. Now, and that is exactly what the problem is. A circle is not a function because it does not pass the vertical line test. So what these two cases correspond to are the top circle, where the y-coordinate is positive, and the bottom circle, where the y-coordinate is negative. Top circle and semicircle and bottom semicircle by themselves are functions, but they're not a function together. So now, in order for me to take a derivative, I'm going to have to take it one sort of branch at a time. But let me rewrite this as a power so I can clearly see what derivative rules to apply. So square root is a power of 1/2. So if I were to now take a derivative of this guy, the outside function is the power. So 1/2 comes down, 4 minus x squared. I subtract 1 from the power, I get negative 1/2, times the derivative of the inside. So this is where the chain rule comes into play. And the derivative of the inside here is minus 2x. Great. So this is just the derivative of the top half of the circle. I still have to do the exact same thing for the bottom half of the circle to produce the derivative there. And this is generally going to be the issue with solving method, is sometimes I will get an expression for the derivative. There's going to be more than one expression for the derivative as the answer. Okay, let's try to think about how would I be able to differentiate that right away. So I'm going to use the dy by dx notation here. We're going to use the prime notation in the next example just to see how that works. But let's start with, I'm just going to take my equation and differentiate it with respect to x. The key here is to remember that this y is actually this thing. So this y has things inside of it. This y right here is itself an onion with layers. So when I'm taking a derivative of it with respect to x, I have to be mindful of the fact that it has an inside. So it is this term that I'm going to have to apply the chain rule to. Okay, let's do it term by term though. So the derivative of x squared is just 2x. There is nothing to it. But we're going to have to apply the chain rule to this y squared. Once again, the outside function is 2, so that's fairly straightforward. The power comes down, gets reduced by 2, but the inside here, y, also has x's in it. Again, like if you solve for it, then you know what they are, but I don't want to have to solve for it. All I have to know is that there is something on the inside, which means I have to apply the chain rule, and the chain rule tells me that once I've taken the derivative of the outside, I have to follow up with the derivative of the inside. The inside here is just y, so the derivative of it is dy by dx. I don't know what it is explicitly, but I don't have to. That's why it's called implicit differentiation. I'm going to take that box and pass it on through the derivative. On the right-hand side, I have 4. A derivative of a constant is just 0, so I have 0. Well, this is actually pretty great news. I've taken the derivative, and what I'm actually after is dy by dx, which is one of the things here, so I can just solve for it. I can isolate it on the left-hand side here, minus 2x, and then I can divide everything through by 2y, so I'm going to get dy by dx is equal, 2's will cancel, minus x over y. Great, and I'm done. This is the derivative of y. So let's compare the two methods. This one is a lot cleaner in the sense that I didn't have to solve for anything. I didn't have to introduce any ugly square roots, and I also really did not have to introduce this split into more than one case. On the left-hand side here, that caused me to end up with 2 different versions of an answer depending on which branch I'm in, whereas on the right-hand side, I have one compact answer. The only downfall to this method, though, is the fact that here, my answer, my derivative, has also both x's and y mixed into it, right? So whereas here, if I start with y equals function of x, then I end up with the derivative being the function of x. Here, I have x's and y's all over the place. Let's take a look at another example and use the implicit differentiation method, but with the primed notation, just to see how that works there. Slope of the tangent line, of course, is a derivative. So this question is just asking to compute the derivative of this function at this point. Great. So let's take a look at this function here. X cubed y cubed minus 3y to the 4th equals 3. Clearly, y and x are all mixed in together. This function is given to us not directly. And there is a problem in that if I could at least, in the previous example, I at least had a choice of methods because I could solve my given equation for y. Here, I don't even have that luxury because the y appears in more than one place. It will be very difficult to solve for it directly. So it's just not even worth the hassle. I'm going to apply implicit differentiation and take a derivative of that as is. And I'm going to use the prime notation this time, keeping in mind that prime means I'm taking the derivative with respect to x. So every time I encounter y, the derivative of y will have to be followed by y prime because y is itself an inside function. So how we're going to take a derivative of this first term here? So the first thing to notice is that before anything else, this is a product. So I'm going to apply the product rule here. So be mindful of the fact that all of the differentiation rules that we already have still apply to these cases. If you have yourself a quotient, you'll have to apply the quotient rule and so on. So the product rule states that I take a derivative of the first thing. Let me actually write this out without proceeding with derivatives first. Plus, I leave the first thing alone, take a derivative of the second thing. So this is what my product rule would tell me. Minus, and then I have to proceed through here. So this minus 3 is just a constant. I can leave it alone and then take a derivative of y to the fourth. And the 3 on the right-hand side just turns into 0. Okay, and now let me actually go through and take those derivatives. X cubed, the derivative of x cubed with respect to x is just 3x squared, so nothing to it. Here I have x cubed and then the derivative of y cubed. So once again, I have the outside function being the cube and the inside function being the y. The chain rule says to take the derivative of the outside function first, and then follow it up by the derivative of the inside, which in this case is y prime. Okay? So every time you take a derivative of something involving y, like y cubed, you have to follow it up by its own inside derivative. Okay? And similarly here, I'm going to have 3, and then the derivative of the outside function is 4y cubed, followed by the derivative of the inside, which is y prime. Great. So let's go back and read what the question is asking. I would like the slope of the tangent line, so I'm after y prime at this particular point. Notice that y prime occurs in 2 spots, here, y prime here, y prime there. So if I were asked for y prime expression in general, I can just isolate those 2 terms on the left-hand side, solve the entire thing for y prime. But in this case, I'm given one particular point. So there's really not necessarily a need for me to deal with all of these unknowns when I can simply plug in the point and then solve for y prime in what remains. Once you plug all the numbers in, you can solve for y prime. And in this case, it should just be a number because you're given a specific point at which to compute the slope. Given a point, the slope is of course going to be a specific number. Okay, I'm going to leave it to you to actually figure out the rest of the algebra here, or if you want to proceed and solve for y prime in terms of all the x's and in terms of all the y's. Implicit differentiation is particularly useful in word problems that involve several different changing quantities, because implicit differentiation specifically tells us how to deal with things that have established relationship, but one is not necessarily solved in terms of the other. So let's consider the next example. Consider a solid spherical tumor. An MRI measures that the tumor is growing at the rate of 0.005 centimeters per month when its radius is 0.4 centimeters. How fast is the volume of the tumor changing at that point? A lot of times, it's not necessarily the size of the tumor that matters, especially when it's small, but rather how fast it's actually growing. Here, we're going to compare the growth of radius, which is a linear measurement, to the growth of volume, which is a cubic measurement. I am asked for how is the volume changing, whereas I am given how fast the radius grows. So first of all, I'm going to need to establish a relationship between the volume and the radius. I'm also told that the tumor is spherical, so we have a relationship between the volume and the radius of a sphere. Volume is 4/3 pi r cubed for any sphere with radius r. Great. So now what I do have, if I were to sort of write down on the side what is the information that I'm given, the information given to me is the fact that the radius is changing at 0.005 centimeters per month. The radius is changing, I'm given the rate of it, and the units should also suggest that I am actually given the derivative of the radius. The derivative of the radius with respect to time, as per units here, is a positive 0.005. I am also told that this is all happening when the radius is 0.4 centimeters. So this is a particular instance in time that I have this information for. Great, that's what I am given. What I want is how fast the tumor's volume is changing. So what I'm after is the derivative of volume with respect to time. Great. Now I have this expression here. All of the things that I am given and asked for are derivatives with respect to time. So I'm going to take a derivative of this relationship with respect to time, keeping in mind the implicit differentiation fact, and that is that this volume is itself changing with respect to time, and this radius is itself also a function of time. Okay, so taking the derivative one piece at a time, the derivative of volume is just the derivative of volume. That's in fact the thing that I'm after. So in this case, we're kind of lucky that the left-hand side is actually exactly what we want. We won't even have to solve for it. What about the right-hand side here? So 4/3 pi is a constant. I don't need to take a derivative of it according to the constant multiple rule. I can take that and keep it. I just need to take a derivative of r cubed. So r cubed, the outside function is the cube. So I take the derivative of outside function first, 3r squared. But then, of course, I remember that r is also a function of time because it's changing with time. So now I need to follow up with the derivative of r. And derivative of r is just dr by dt. Okay, once I have that, again, I can see what it is that I want. I want dv by dt, so I actually want this left-hand side as is. And here, I just need to plug in all the known values into the right-hand side of my equation. So I need to plug in all this given information into here, and I'm going to have myself an actual answer. So we're going to plug in r equals 0.4, and dr by dt was 0.005. Okay, so altogether, as the answer, once we've computed it all, and you can plug in pi equals 3.14 or some kind of approximation of it, this should work out to be 0.03 units per month. What are the units? Let's take a look at here. It's the units of volume, and volume was radius something times radius cubed, so the units of the volume are going to be centimeters cubed, and the units of time were per month. So when the radius is growing at this rate and it's measuring 0.4 centimeters, my volume is changing at 0.03 centimeters per month.
Let's take a look at a few more examples of how to apply the chain rule and the related rates ideas to other problems. So in here, in this example, we're going to be talking about the Dubois and Dubois formulas that give an approximation of human body surface area in terms of the mass and the height of an individual. This is the actual formula. Now, this formula is actually useful for things like determining the amount of burns, for example, in burn victims in terms of the surface area, and that helps figure out how dangerous that amount of burnt skin actually is. So here we have a situation where Amanda, who currently weighs 65 kilos and is 1.6 meters tall, starts training for a marathon. We are wondering how fast is the surface area of her body changing, so whether increasing or decreasing is something we're about to find out, when she is losing 0.9 kilos a month. So we have her current weight, her current height, so the M and the H that are the starting point, and we also have this particular value. We know that she's losing 0.9 kilograms a month. So maybe before we start actually doing anything else, we have to think about how can we write that in terms of the mass, the height, and the surface area. So she is losing this amount of weight. Weight, of course, corresponds to the mass here, and this is happening per month. This is the rate of change of her weight per month. So this is equivalent to saying that the change in mass per unit of time, which is given to us as the month here, is going to be 0.9 kilograms per month. Now, if you look at this for a second, you should probably find out that this is not exactly correct yet. The one piece of information I have not included yet is the fact that she's losing weight, and that has to be portrayed in this expression by making the value negative. So we have that is how fast her body mass is changing. We also know that her current body mass is 65 kilos and her current height is 1.6 meters. We are interested how fast the surface area is changing. So what we would like to know is the rate of change of the surface area with respect to time. Once we have our information written down like this, it's easier to see what we're after and what do we actually know? We're after the derivative of this entire expression, and we know that the mass in particular is also a function of time because it's changing with time. So we need to take a derivative of this entire expression with respect to time. The first thing to notice, of course, is this is first and foremost a product. So for us, the first thing to do is apply product rule. So let's write it out. I'm not actually going to take derivatives yet. All I'm going to do in this first step is write out what it is that I am doing. I can leave the 0.2 out because it's a constant and I can just take it out and take a derivative of everything else. And now I have to apply the product rule to these two pieces of my function. So the product rule says take a derivative of the first part. So again, I'm not actually going to take derivatives. I'm just going to record the fact that I will be taking them. And then according to the product rule, I leave the second part alone. Plus, I leave the first function b and take a derivative of the second one. Now, again, the prime notation isn't ideal here because I actually do have to keep in mind that I'm taking a derivative of that with respect to time. And so these, the mass and the height, might be functions of time. I know that the mass certainly is, and I have to think about whether or not the height is. Okay, so let's now take derivatives. Here I have to take a derivative of this particular expression. So the first thing to do, of course, is just apply the power rule. The power comes down in front and gets reduced by 1. So I'm going to get 0.425 m to 0.425 minus 1. But then I've taken the derivative of the outside function, but my inside function m is also a function of time. So I have to follow this up with the chain rule multiplying by the derivative of the inside function, the dm by dt. Okay, now this just corresponds to my derivative here. So this is the derivative. And then of course I better not forget that this entire expression was followed up by the multiplication by h to the power of 0.725. Next, I'm going to do something very similar to the second half of this expression. Pause the video and see if you can do this yourself. So first I'm going to rewrite the m to the power of that is not being taken derivative of, and then I have to take a derivative of this. So what do I have here? I have to bring the power down. I have to reduce the power by 1, and I have to think about the fact that height is also a function of time. I'm taking a derivative with respect to time, so I have to go through ds by dh by dt in order to actually get to the final variable. So I have to follow this up with dh by dt. Okay, so this is a derivative of my h to the power of 0.725. Okay, so again, remember that in the chain rule, I have to go through all of the steps. If I'm taking the derivative of s with respect to time, but it's given to me using the other functions, I have to take a derivative with respect to that function first, which really means applying the outside, in this case, power rule, and then follow it up with the derivative of the inside, which in this case, I will actually just have the values off in the next step. Okay, so here now I am in good shape because everything here is something that I already know. Look, the value for m is 65. So I'm just going to mark up what it is that I know. M is 65. The value for dm by dt is minus 0.9. So this is something I already know. And the value for h is 1.6 meters. That's how tall Amanda is. And then, of course, here again, I have that the value for mass is 65. The value for h is 1.6. And now I have to think about what this value is. It's not actually written down in what I explicitly know just yet. So what is the derivative of height with respect to time? How fast is Amanda's height changing as she's training for a marathon? Assuming Amanda is a grown woman, and children generally do not train for marathons, Amanda being my best friend is a grown woman, her height is not going to be changing with her training. So the rate of change of her height with respect to time is going to be 0. Once you have all of these numbers, you can just plug them in and you're going to get a value, which is 0.001, if I've done my calculations correctly. And what are going to be my units? Going back to this notation, I have surface area with respect to time. And surface area has meters, mass, and height. So you have to really think carefully here about what the units are going to be. I'm going to write them down, but I encourage you to work it out and think about how the actual components add up to the units that we're after. It's going to be meters squared, and the units of time here are, of course, months, because that is what we've introduced throughout. So my conclusion is that Amanda is, her surface area of her body is changing at this value. And being negative, it means that it is actually decreasing. So Amanda's surface area is decreasing, and the rate is given to us by the number minus 0.001. Let's take a look at this next example of looking at the average height of girls in the United States of America. It is given to us as a function of age in months by the data in this graph. So the red points are the actual data, and we can see that they can be represented fairly well with this linear function that is in blue, given by this particular formula. Notice that the age here is in months. So for example, at 120, we're actually at 10 years, not 120 years. We are also given the fact that the relationship between height and weight in this age group is given by this particular formula. So this is linking the weight, and the height. Sorry, apologies. This should be h here. Okay. What are we asked to find here? We're asked how fast are the height and weight change at the age of 10 years. So at 10 years, we have this point right here. This represents 10 years, and we're wondering at that point, how fast are the height and the weight changing with time? So, first of all, what it is that we need to know in terms of the actual variables. How fast is the height changing means that we're after the derivative of height with respect to time. How fast is the weight changing? That means that we're after the derivative of weight with respect to time. And now with this information, we can actually go back through the problem and see how we can derive those values. So let's start with the height. dh by dt. I actually have a formula here for the height in terms of the time. So this is going to be very straightforward. All I actually need to do is take a derivative of this expression. And I can see here that it's a linear function, so it's going to be really quite easy. The derivative of 32 is 0, and the derivative of 0.185t is simply 0.185. So I can say right here that dh by dt is equal to 0.185. And now thinking of units, the height was measured in inches, and the time was measured in months. So we have ourselves inches per month. Now, this is not surprising that it's constant because, again, the data here is modeled by a linear function. And of course, a line has a constant slope, resulting in a constant derivative. Now, what about the weight in terms of time? So I have a formula for weight in terms of height, but of course, now I needed the derivative in terms of time. So I am going to have to go weight, height, time. And that is, of course, an application of a chain rule. I'm going to write this out as I'm going to be able to take a derivative with rate with respect to height, because that is the formula that I'm given, and then follow it up by the derivative of height with respect to time. Again, if you prefer the prime notation, what we have here is that the weight is a function of height, which is a function of time. So if I am to take a derivative of that, I have to first take a derivative of the outside function and follow it up by taking derivative of the inside function. Okay, I'm going to stick with my Leibniz notation, the fractional notation, and carry on through here. So first of all, what is the derivative of weight with respect to height? All I have to do is take a derivative of this formula, keeping in mind that h is in fact my variable. So doing that, I have to rewrite my constant, and then I'm just going to apply the power rule to h to power 2.6. So times, 2.6 times h to the power of 1.6, right? Again, subtract 1 from the power. And then I have still the derivative of the inside, so dh by dt. If you're thinking of that in terms of the related rates, that's your normal chain that follows all of the related rates, right? I have taken derivative of my function as is, and I have to recognize that h is also a function of time, so I have to follow it up with that derivative. Now, what do I have? I am interested in this, of course, overall expression. I know that dh by dt is this value, so I can simply plug that in. So dh by dt is 0.185. But what about the actual height here? Well, at which point am I asked to calculate this derivative? I am asked to calculate this derivative at the age of 10 years. At the age of 10 years, this is where I have t is equal to 120. And according to this, I can actually calculate the value of the height using the model for the height that I am given. Okay, so this is a little bit of more calculations that can be sometimes expected. So here I have to actually figure out that height at the age of 120 months is equal to 32 plus 0.185 times 120. So this all in all will be 54.2, which, sort of eyeballing it from the graph, looks approximately correct. And then putting all of these numbers together will give me 0.7 as a value. And what are the units? Going back to this notation, I have weight over time. Weight is measured in pounds. Time is measured in months. So pounds per month. Again, I can interpret this as increasing or decreasing depending on whether the value is positive or negative. The number here is positive, which means that this is an increasing rate of change. So both height and weight are in fact increasing at the age of 10 years. Again, not very surprisingly, given our experience with how children grow up, and also not surprising given the function that we have. For this next example, let's take a look at a more of a setup that we will have to work our way through. Notice the difference between the previous example and this one is we have no formulas in this entire problem statement. So whatever connections between the variables exist, we will have to come up with them ourselves. So now that we have an expectation of having to build a model, let's read what this is all about. A spider is moving horizontally, so not according to the picture, across the ground at a constant rate. Okay, so I have some kind of ground level. Let's start making a picture. And I have a spider and it is moving horizontally. Okay, so this is my spider. Now, next up, we know that he's moving a constant rate. That's good to know. He is pulling a thin silk thread with it. One end of the thread is tethered to a vertical wall at height h. So we also here have a vertical wall, and we know that the actual height at which the thread is attached is h. And my spider is pulling on the other end of that silk thread. Okay, so this is a wall, this is a movable, and this is a thread. And as the spider is walking, the thread keeps stretching. Okay, at some point it's going to break, but it's actually very stretchable. Now, this point does not move. The other end moves with the spider. Determine the rate of elongation of the thread. So the thread starts off with a certain length. let's for example call it L. But this length isn't constant. As the spider moves along, the length keeps changing. If the spider decides to move in the opposite direction, maybe the actual thread will start shrinking as well. We are asked to determine that rate at which the thread is actually extending or shrinking. So what is it that we are given? Let's go through all of this information again now that we have some variables written out on our diagram. Spider moves horizontally at a constant rate. We don't have a way to record it yet. What does it mean to move at a constant rate? So for example, if he moves at a rate C, what does that mean to move at a constant rate? It means that the rate of change of its position is constant. But so far, we have no way of determining the position of our spider. So let's say if the wall is at sort of the origin at point 0, then the spider can be at some distance x away from the wall. And then, as the spider moves along, its distance from the wall is changing with the rate constant c. So the derivative of the distance, which is x, from the wall with respect to the time is going to be constant. What is it that we want? We would like to determine the rate of elongation of the thread. So how fast this is changing. So the derivative of L with respect to time. So now the problem is I don't have any way to connect L to H or X just yet. I am going to leverage my diagram and my knowledge of geometrical figures in order to come up with such a relationship. And in this case, it's pretty straightforward. I can see that given the fact that the wall is vertical, we're going to have a right angle triangle here. I am able to apply a Pythagoras theorem to this triangle. So by Pythagoras theorem, I can come up with a relationship between these variables. So specifically what I have is L squared is equal to x squared plus h squared. Now, of course, I can write this out as L is equal to square root of all things, but remembering that I'm going to have to take derivatives, taking the derivative of a square root might be too cumbersome, and it's probably easier to leave everything without any kind of fractional powers. So now, let's actually go ahead and take a derivative of this entire expression with respect to time, because that is both the information that is given to us and the information that we want. Okay, so what I'm going to do is I'm going to first, just as highlighting the fact that that's the step that I'm taking, I'm going to rewrite this and I'm going to signify the fact that I'm going to take a derivative of that with respect to time. So what do I have on the left-hand side? L squared. The derivative of L squared is 2L. And of course, L itself is a function of time, so I have to follow this up with dL by dt, which is great because that's in fact the value that we want. Equals, and then I have to proceed similarly on the right-hand side. The derivative of x squared is 2x, but x is a function of time, so I have to follow this up by the derivative of the inside, which is x, or dx by dt. And similarly, h squared, the derivative is 2h. H is a function of time, so I follow up with the derivative of its inside, dh by dt. Okay, now let's see what we have here. I know that this expression is equal to c. That is what I'm given. The spider moves at a constant rate. And what about dh by dt? So is the height of the wall here changing? Well, no, it does not move and it does not change. So I know that this expression is going to be equal to 0. And I can write down the justification for that since the height does not change. And now that I have that all together, I know that then this whole piece is going to go away because it's times 0. I am after this expression right here, so I can in fact solve this equation for dl by dt. Okay, so what are we going to get solving for dl by dt? if you go through the steps carefully, I'm going to divide both sides by 2L. And so altogether, I'm going to end up with dl by dt is equal to x times c divided by L. Now, I'm given no numbers here, so I can actually leave it as that. I can also make it a little bit simpler because likely the length of the thread is not something known to me, but I probably know how far the spider is away from the wall and how tall the wall was in the first place. So I can actually solve for this L using the exact same relationship as before. So again, this will depend on if this exact problem is given to you, but with some numerical information, but this might also be helpful to have L expressed in terms of x and h. And that is all we're going to have. Notice that in this case too, I'm assuming that spider can move left or right here. And so depending on whether c, the rate of change of x is positive or negative, the entire value here is also going to be positive or negative in the exact same way. So if c is positive, it means that the spider is moving away from the wall, which will result in the elongation rate also being positive, which corresponds to the thread length increasing. If c is negative, he's moving towards the wall, which will correspond to the length of the thread shrinking. Okay, so the difference between this problem and the previous one is the fact that we had to come up with the relationship to differentiate ourselves, whereas in the previous problem about children and their heights and weights had all the information, all the functions and relationships that we needed given to us. Now on this last slide, you have 2 more problems to actually practice the implicit and chain rule information and differentiation with. So take a look at those. These are nice problems as extra practice.